Okay, really. Oh, there it is. No problem.
Okay.
Hello, everyone. So today's seminar is from Lara Gatto. She holds a bachelor's degree in physics from the. There is what?
Oh, okay.
Hello, everyone. She holds a bachelor's degree in physics from the Federal University of Rio Grande do Sul, which was obtained in 2018, and a master's degree in physics from the same institution completed in 2020. She earned her PhD in astronomy from the Federal University of Rio Grande do Sul in 2025, and following her doctorate, she worked as a postdoctoral researcher at the Heidelberg University in Germany between 2025 and 2026, supported by the CAPS Pro Fellowship. Her research focused on quantifying the impact of active galactic nuclei on their host galaxies. So I'll give you the floor.
Hi, everyone. My name is Lara. Today I will talk about AGN feedback, star formation, and the environment of an extremely red quasar at Galactic Nuclei. Okay, so one active galactic nuclei is a nucleus in the central region of a galaxy, where the supermassive black hole is actively accreting matter through accretion disk. This accretion disk releases an amount of energy reaching about luminous volumetric in the order of 10 to the 42 to 10 to the 48 ergs per second. This emission is across the entire electromagnetic spectrum, from X-ray to radio, and have no stellar origin.
This means. Here we go.
Okay. And the AGN is located in the center of the galaxies in a compact volume. To understand the AGN structure, we have the unified AGN model. When you have the black hole, supermassive black hole at the center of the galaxies, we have one accretion disk around it. We have a broad line region close to the accretion disk, and we have a torus around the broad line region and the accretion disk. And in more distant regions, we have the narrow line regions. And you can see different types of AGN depending on the observer side orientation of the observer line of sight relative to the AGN. So we can have a diverse AGN zoo depending on the orientation that we're looking to the AGN and the luminosity. You can have the safer 1, safer 2, hot dogs, blazar quasar, extremely red quasars, and go on. Oh, it's on the way. It's important to study AGN because you can see that we have a co-evolution between the supermassive black hole and the host galaxy. So the accretion rate, the matter accretion rate of the supermassive black hole is linked to the star formation rate. We can see here in this graphic that in the star formation history, the black line, and the star formation supermassive black hole accretion rate in red is linked with the peak in between 2 to 3 redshift. This is called the cosmic null epoch in this region where we have the both star formation and supermassive black hole accretion at the highest rate. We can also see a co-evolution between the AGN and the host galaxy because we can have the gas inflowing in the galaxy can lose angular momentum, and go to the center of the galaxy, triggering the supermassive black hole, and also trigger the star formation in the galaxy. So we call this process laser feeding. And after the black hole is triggered, this AGN can release this amount of energy in wind, jets, or even heating the gas around the AGN, suppressing the star formation rate. This process we call the feedback of the AGN. Today, the main goal of this presentation is to connect the role of the AGN in the host galaxy across different cosmic scales, from nearby galaxy to the dense environment of the extremely red quasar at cosmic nuclei. So I will start to talk about the nearby universe, quantify nuclear star formation, and map the disturbed gas in these AGN host galaxies, and also estimate the AGN impact in this galaxy. In the end, I will go talk about a little intercosmic epoch, where we will talk about the extremely red quasar J1652 and characterizing the environment of this quasar. To study the nearby galaxy, we use the MaNGA data from MaNGA Cube's data by Rogério. The MaNGA project observed about 10,000 galaxies in the local universe, and the ER field size have about 90 to 157 fibers, and the wavelength is in the optical, so we can analyze like O3, H beta, H alpha, heterogeneous lines in these galaxies. And each fiber of the data was 2 arcseconds. To select one AGN sample, you use BPT and one diagnostic diagram, and we find 2,093 AGN hosts by this method. And to compare this AGN, the impact of the AGN in the host galaxy, we also select a control sample. We select 2 control galaxies for each AGN with the same morphology, mass, redshift, and inclination. In the end, we have 4,085 inactive galaxies. You can see here this histogram, the redshift, the stellar mass, the stellar dispersion is similar, but the luminosity of the AGN in the red is more high. To get the star formation rate of this galaxy, you use a starlight code that uses for stellar population synthesis to obtain this galaxy star formation histories and the star formation rates. We also we subdivide your AGN sample in 4 bins according to the luminosity, O3 luminosity. AGNs that have 3.8 to 10 to the 40 Hertz as classified as strong AGN, and the others are weak AGN. We also classify as early type and late type. So we have 4 bins: strong AGN early type, weak AGN early type, strong AGN early type, strong AGN late type, and weak AGN late type. This is not working more. Okay. When you see the histograms of the nuclear star formation rate of these galaxies, we can see the most difference about star formation rate is in the strong AGN early type. We can see here the AGN is the pink one, and the control is the blue. So you can conclude that even in small difference, in all bins, the AGN have higher star formation rate in the center compared to their contours. And when you can see the star formation radial profile of these galaxies, We can also see the strong AGN early type and strong AGN late type, both early and late type, have a higher star formation rate in the saber compared to the contours. And the difference between radial profiles in the weak cases is not so higher in the center, but you also have a higher. Oh my God! You also have a higher star formation rate in the AGN. We also measure the black hole accretion rate in this AGN. So we can see here, with a higher star formation rate, we have a higher black hole accretion rate. We have a weak correlation here in the black lines. This work is in agreement with the other literatures. And compare your star formation rate in AGN and control. We also compare to the star formation main sequence. To get the star formation main sequence, you take 10,000 galaxies from MaNGA and plot this graphic here, where the gray contours is the star formation galaxies. So you can find here your star formation main sequence in blank. It is in agreement with the other authors in the literature. And when you put your AGN and control galaxies in the same plot, we can see here that the distance from the AGN to the main sequence is small value. Like this graphic here, we can see that the AGN is more close to the star formation main sequence compared to the contours. It's about the star formation, AGN star formation is about 2 times higher than the contours in this case here. So if the mean values of the AGN in contours is below the star formation main sequence, but the AGN is more close to the main sequence compared to the contours. So after I would now I will talk about the disturbed region of this nearby AGN, and take the same sample. We measure the WA for this AGN in red and the contour in gray. You can see that in the AGN we have a more disturbed gas compared to the contours. So here we define one value, W80 cut, that is the mean of the distribution of the contours plus the standard deviation of the distribution of the contour galaxies. And we find a value of 315 kilometers per second. So you assume that the region that have W80 values higher than this value here is disturbed by the AGN. You can see here. So we define a kinematic disturbed region that is composed by this spaxel that have W80 higher than this value, and also are classified as AGN or composite in PPT diagram. And compared to the extended narrow line region of this AGN, that is the region where the spaxels are classified as AGN or composite in the PPT diagram. You can see that the KDR region in blue is about 57% of the extended narrow line region. So the extended narrow line region is the double of the value, the distance of the disturbed region, disturbed gas by the AGN. We also compute the kinematic impact of this AGN and the host galaxies by the mass outflow rate and kinetic power. And you can see in this work here in the blue, in the black points, it's the end filter region corresponds to the low luminous end of the well-known relation here. So after talking about the nearby galaxies and the impact of the AGN in the host galaxy, I will talk a little about the Lyman-α emitters around a extremely red quasar J1652. So one extremely red quasar is representing a short-lived and violent transition phase in the life cycle of massive galaxies, the blowout stage. So this type of quasar is classified as that have extremely red colors. Intense dust obscure the nucleus. We have extreme luminosity with volumetric luminosity higher than 10 to the 47 Earths per second. It is among of the most luminous objects known in the universe, and also have extremely kinematics, with O3 outflow up to the 4,000 kilometers per second. And the environment that this quasar is located is possibly in the proto-cluster and overdensity environments. And also they are found in the redshift range of the cosmic moon. This blowout phase is where a red quasar, because an obscure red quasar, is started to get blue. So the black hole in this case is rapidly creating matter. This quasar releases enormous of energy. It is energy drives powerful outflows that expel the dust from this galaxy, and it starts to, in the center of the AGN, starts to get, we can start to see the AGN in the center. So this case of J1652 is a well-known quasar at the redshift 3. We have plenty of studying with James Webb, the Hubble Space Telescope. This quasar is located in redshift 2.9, almost 3. Have a volumetric luminosity. Have a volumetric luminosity of 5 to the 10 to the 47 Earths per second, and a stellar mass of 10 to the 11 mass solar mass, and have a star formation rate above 200 solar mass per year, and a black hole mass about 9 log of mass hole 9, about 9 to 10. And here you can see this quasar is located in this region, and here we have a zoom in the quasar, and you can see a complex O3 kinematics and morphology here. The different colors is different velocity of O3. You can see the most blue one here is the most negative velocity, O3 velocity, and the more red is more redshift velocity. You can see a disturbed region around this quasar. We also observe this complex morphology, and this is implied that this quasar resides in a very dense environment with several companion galaxies. In this work, we find 3 companion galaxies. This one and these 2 here is the companion galaxies. Probably we are looking at a core of the star formation, a star cluster of galaxies. Using NIRSPEC data, we find O3 emission extended to 10 to the 15 kiloparsecs, and a disturbed biconical morphology and radial velocity about 500 kilometers per second, and a velocity dispersion of O3, of course, O3 about 1,000 or above here. It's a really disturbed quasar. More recently, Caroline Bertens find with MIRIS data, she find 18 spectroscopy confirm members, galaxy members in this region in the field of view of the observation, including two quiescent galaxies. Here's the position of these companion galaxies, and when we plot the position in 3D, we can see we have two structures almost colliding. So we can name this proto-cluster structure as step, the step proto-cluster. So my work focuses in define Lyman-α emitters. Lyman-α emitters are galaxies where you can find a strong Lyman-α emission, and we can easily see these galaxies in the universe at about redshift 2 to the 7. And Lyman-α emitter galaxies are vital probes for detecting in young and star forming galaxies at high redshifts. Typically, the line profile of Lyman-α is asymmetric or double peaking, a result of the radiative transfer in the optic media, probably outflow or complex kinematics. Detecting Lyman-α emitters are useful because these galaxies trace cold gas and low mass galaxies. So you are able to map the quasar more, the environment of the quasar with this type of galaxies. This type of galaxies is useful to identify proto-cluster members and probe the local ionization state of these regions. So to do this, I use MUSE data, a multi-unity spectrum explorer at VLT telescope, and we have a field view of 1 arc minute per side, and a spectral cover of optical, but we are observing redshift 3, so you can see the ultraviolet spectrum. To detect the Lyman-α, I constructed one pipeline. The first, I subtract the continuum of this cube. You can see the raw data. You can see this really bright emission here around the quasar. Here is the quasar. So, but when we look for this spectrum, this is a star. So by removing the continuum, you can remove these points here that are not a real emission. So in the end, you have this beautiful thin map. To more easily detect the Lyman-α emission, we needed to construct to make a narrow bands. So I make 80 narrow bands with a width of 10 arcsec each. So you can cover all. We can cover all the Lyman-α emission. Here is the example. This is a Lyman-α emission for the quasar. So you can cover one region around the Lyman-α emission of the quasar to search for Lyman-α emitters galaxies companion to the quasar. After making a narrow band, in each narrow band image, we analyze independently. So I run Monte Carlo simulation, performed 2000 realization. For each iteration, we add the Gaussian noise to the data for the variance map. So we run a well-known software, Python code, DAO Star Finder, to find a little small emission of Lyman-α in all this pseudo narrow band image. After that, DAO Star Finder gives us the position, the shape parameters of each detection, and use BD scan. We group this this detection together to make one. And if this, you also have a reliability estimation when you can, if the same Lyman-α emission appear more than 40% of the simulation, we confirm that this is a real Lyman-α emission, not a regular emission of Lyman-α. After that, we extract the spectra of these Lyman-α positions we detect. So you can fit a double Gaussian fit to this Lyman-α profile. You use double Gaussian because sometimes you can see the Lyman-α emission is a double peak or have a wind on the blue side. And you only keep the Lyman-α emitters that have signal to noise higher than 5 in the end. So in the end, we will only detect 31 Lyman-α emitters around this quasar. So I classified this emission as the galaxy, the quasar. The galaxies here is the one particular case that I will talk another time because this is complex. We have one galaxy at redshift 1.9 and one Lyman-α emission at redshift 3, almost together. So in your line of sight, we can resolve this. So you have. So I exclude this, but this is a really interesting case. We have the quasar itself. I classified the near Lyman-α emitters that is located with a project distance about 40 kiloparsecs from the quasar. Field of view strong Lyman-α emitters that are located in the distance higher than 40 kiloparsecs and have luminosity greater than 3 to the 40. 10 to the 42 30%. And then we field view with Lyman-α emission is located in the field of view and have luminosity smaller than lower than this value. So I also have a confidence level. Here we have 3 confidence level using the signal to noise ratio. This is we'll present some 3 examples only because of the time. Here we have the Lyman-α emitter number 5. It's classified as a near Lyman-α emitter. So here located in the 15 kiloparsec distance from the quasar and have a velocity offset about 150 kilometers per second. So you can see here the Hubble Space Telescope image, and here in this rectangle, you can see the MUSE narrowband detection. So this Lyman-α emission is in the Lyman-α nebula for the quasar, and we also have detection in the nearest data in the same position. So here we can see the nearest data, the quasar here more bright. On top we have 1 star, and here it is bright blue is the Lyman-α emission 5. So when you see the spectrum, Lyman-α spectrum, you see a double peak in the Lyman-α emission. Probably one peak is from the galaxy, and another from the Lyman-α nebula from the quasar. So you need to. It's hard to distinguish. Lyman-α emitter number 9 is also a near Lyman-α emitters in a distance about 30 kiloparsecs and velocity set 100. So it's located here. This is the Hubble Space Telescope image, and here we have the narrowband, MUSE narrowband of this emission here, this little galaxy. When you see the spectrum, you also see a double peak in the Lyman-α emission. And another case is the Lyman-α 40. So it's a field of view with strong Lyman-α emission located about 100 kiloparsecs away from the quasar. It's located in this direction. This is the quasar, so just for remember. And in the MUSE narrowband, you can clearly see one emitter galaxy here. And again, this is the beautiful Lyman-α spectrum. When you put all these 31 Lyman-α emitters in 3D, you can see here in the star is the quasar. The color is the type that I classified, and the size of the marker is the Lyman-α luminosity. So this is the galaxy that I find. So the cyan is the Caroline detection that I comment in the nearest data. When you put this information in a 2D view, we can see that the distribution of the redshift here, the closest more when we are more close to the quasar, we have more redshift similar to the quasar. So this is and in the center you also have more luminosity. So when we are close to the quasar, we have more luminosity Lyman-α emitters, and when you are away from the quasar, we have more fade Lyman-α emitters, and also with velocity offset. When you are close to the quasar, you see a positive velocity offset in a small number, and when you go out for the quasar, you can see more bluish velocity offset from the quasar and more dispersed way. And you can see in this image that we have a lack of Lyman-α emitters in a near distance of the quasar. Okay. Here. You can see in this region you only find 2 or 3 Lyman-α emitters. You have, when you put this project distance of Lyman-α emitters, you have 2 peaks. One more concentrated in 55 kiloparsecs away from the quasar, and another about 2040 away from the quasar. And we have this gap that we find less Lyman-α emitter. So you have 2 main scenarios about this. You can see a superposition of 2 populations, when you can see an inner population more associated with the quasar, and you can also see and the other population is more a background population, like a random distribution of the galaxy. So when you run a QS test for the Lyman-α emitters that have a project distance higher than 60 versus a random 2D distribution, we can find that this scenario is possible. You cannot exclude this. This gap probably will be a natural transition between 2 components or two environments. Another hypothesis, probably the lack of Lyman-α emitters at this region it's a suppression of the star formation rate in this region, due by the quasar feedback. Because remember, Lyman-α emitters galaxy is a star-forming galaxies, youngest with youngest stars. So in probably in a time ago, the quasar the AGN ejected a radiative feedback can evaporate or suppress the star formation around the halo of this quasar in this region. Here, just put the distribution of the redshift and velocity offset for this 31 Lyman-α emitters. We can see the quasar redshift is this here in 0. The velocity offset is in 0. So you have a high range of velocity offset. Velocity offset, you can say that the different redshifts. So the quasar here is here, the field view of the MaNGA. So the redshift tells us that the distance in this direction. So positive, we are in this direction, negative velocity offset, we are back of the quasar. So we have galaxy in the front and in the back of the quasar. So this is the histogram of Lyman-α galaxies. Is a bias because of the classification. We also compute the Lyman-α overdensity. When you measure the number of Lyman-α emitters per volume, we can compare. We have this. I forgot the name of this letter. The 5 observed. So we can compare this this value with the shatter function from this paper, this yellow line here, and we can see that. And you also make a 3 beams of velocity offset window. Like we can take the galaxies between 2,000 kilometers per second, galaxies between 4,000 kilometers per second, and galaxy Lyman-α emitters 6,000 per second, kilometers per second. So you have different volumes of the sky to compare this Lyman-α overdensity in this region. And you can find here in the green, we are looking for the more closed with 2,000 velocity offset interval. And when you, so the number of density is higher when you look for more close to this to the quasar. When you add more volume, the density is getting low. So in the summary, we find 31 galaxies, Lyman-α candidates, 29 excluding the galaxy and the quasar itself. We have a nuclear concentration around the quasar. We have an extremely overdensed region around this quasar. Consider only the galaxies with a velocity offset between -200 and +200 kilometers per second. This quasar is among of the highest high-Z overdensity region, consistent with a massive proto-cluster formation. So you also observe a gap of Lyman-α emitter in that intermediate distance. Probably this is a transition between the closed galaxy and the random background, but probably also feedback suppression, star formation. We also confirm together with the nearest data that find 18 member galaxies plus the 29 galaxies that I find. We can see that the static proto-cluster is a huge proto-cluster at this redshift. The summary: AGN does not quench immediately. AGN hosts have 2 star formation higher than the contrast. Both share the same gas reservoir, like the gas that accretes the supermassive black holes. Also engage to star formation rate. Feedback is real, but in your case that we are looking for the nearby galaxies, low luminosity AGN, it's maintains mode. Extremely red quasar residing in the extreme environment, and the multi-scale perspective is essential to understand the detailed picture.
Do we have any questions for Lara?
I have.
First,
You can go first.
So it was a really interesting talk. I have 2 questions which are sort of connected. Maybe I missed this point, but why is when you're measuring the velocity offsets, why is the particular quasar a reference? will the results change if you take the reference somewhere else in the middle between the two groups that you observe?
Okay. Again. Two slides. You mean take so you have this is velocity offset.
Yeah.
So I take 2000 here because in some literatures they say that 2000 the galaxies are associated with the proto-cluster needs to be that needs to have inter range of these values. If this galaxy is located with higher velocity offset from the center of the quasar, is not so well. It's not in the proto-cluster. It's outside. So in the same in this, each literature says different things. So this is the more you can see the proto-cluster. Here we can see like a extended environment out beyond the proto-cluster. And this is a more large picture.
And has there been any high energy study for this region? Because maybe there's a potential well in the middle or something.
And you need
they're like X-ray studies.
So for this galaxy, we have observation in Alma, Miris, and Nirspec, Niris, but you don't, for the entire environment, we only have this data. So you needed to study the environment of the quasar more with another data. But with the nearest, Caroline find 80 galaxies around this quasar, but we're not able to see the large X-structure yet on this case.
There is no X-ray.
X-ray.
No, X-ray.
Just for the quasar.
The
quasar. Just the quasar. Okay. Focus on the quasar, we have more data, but the over structure, just the MUSE and the nearest.
So I was wondering one thing. If you're proposing that the quasar suppresses star formation in nearby galaxies, why at the intermediate scales not close to the quasar?
We think about this. We don't have answer. It's just one idea that we and the group have. So we need more data in the other wavelengths to look if you find another type of galaxy in this region. Like if you find a quiescent galaxy in this region, maybe this is a more strong, say, that just a lack of star formation galaxy in this region. Probably, I like more the idea that we have two populations not connect. I like more this idea.
And another thing about your last slide of the conclusions. So you mentioned there that star formation branching occurs on scales of 10 to the 8 to the 10 to the 9 years. And this is much longer than an AGN duty cycle. So could you say that, can you say really that the AGN had anything to do with it, as the time scales are so different?
I forgot to say. Sorry. We can talk later. Another question? Comments?
No more questions? So let's see. Okay.
So I didn't understand what you were asking. Could you please?
So the AGN duty cycle, it's like 10 million years at most. But you are saying that the quenching occurs on scales of 100 million years to 1 billion years. So they are very different. So it doesn't make much sense to expect that the AGN has something to do with it, at least in this case.
If you have like a lot of duty cycles in sequence,
Yeah.
connecting,
Yeah. So yes, exactly. Then you need some kind of cumulative effect, but it goes against the scenario that you exposed at the beginning, that you have some kind of blowout. Because if it was a blowout, it should be very sharp.
But it is for a nearby galaxy, not for them.
No, but you expect on the quasars that I read that are much more luminous, as you said, to be for sure a blowout. But if you're not finding that,
I didn't get what you don't find the blowout.
so because if it was the blowout, the quench star formation, the time scale of quenching should be very short, and it's not.
Because it's a bunch of energy.
But how I calculated time scale of the quenching there?
You need to look at young quiescent galaxies. If they show a pulsar burst spectra, then you can say that it was fast. Otherwise, it's a slow decline.
So you say that they should be younger, so she has the ages of the galaxies, and it's not young enough. It's too old. Is that what you
Yeah.
But these are very local universe galaxies, so it would be tiny.
Yeah.
It's not a blowout. It cannot be a
Well,
blowout.
what is just
Yeah.
Like more recent, it might be something that is heating the gas and accumulating. And
Yeah,
then
no.
that is why it's quenching.
Yeah,
So
I agree.
it's actually not directly connected with the quasar.
Yeah, no, I agree. It's just that, so this is something to think for the future. That when you present how AGN feedback occurs, maybe you should put two scenarios, not one.
Yeah.
But even for the quasar, I think it's very hard to believe that there is a blowout because it's a starburst.
Yeah.
And when Carolina was here, I even mentioned that if you look at the image, it's clearly interacting. So these many O3 components could just be tidal tails ionized by the quasar, not an outflow. So you cannot discern which case.
Yeah.
So it's very hard.
But the profiles sometimes double click, so it shows disturbance.
Yeah, but it could be something on the front or something like that. So.
I mean, same cases that Lyman-α emitters, because this quasar also has a Lyman-α nebula. That is my goal to study in the next months. So sometimes it's hard to disentangle if this is a galaxies in the middle of the Lyman-α nebula from the quasar or not, because you have double peak, two distance double peak, like one for the nebula and for the Lyman-α galaxy. Minimally, always doing it.
Any more comments, questions? If not, let's take that again.